Okay, so yesterday some of us were in here talking about pbdR, and I was going to be talking about that too. So we decided, Drew and I decided to switch from the original plan. He was going to start talking about RCPP, and I was going to talk about pbdR. So I will. So we switch anyway, just to keep talking about that. Just again, a little bit about the pbdR project. There are really four of us. I'm the third one that you're meeting. You've already met Drew, Wei Chen, and the fourth one is Pragnesh, who is also at the Joint Institute for Computational Sciences, and he's not here, but anyway, and the project really. Everybody contributes, and it would not have been possible without getting all four of us together. It was sort of the critical mass of all four people that everything started to move very quickly. So what I'll be talking about, first there were a lot of questions about where do the different pieces of parallel R fit in. And so I'm going to talk a little bit about that. Then I'll say a little bit about data input. Then really the thing that I was going to talk about originally, and that's the principal components, plot ensembles in parallel. And I don't know if I'll get to this. We'll see. Rearranging data. So a quick overview. We'll begin with parallel hardware. I find this useful with audiences, non-computer science audiences, that basically there are three flavors of parallel hardware. And just to make things look familiar, your laptop is these two put together. Okay, you have a multi-core chip in there with 2 or 4 cores, and you have a graphics card. And that's your laptop or your desktop. If we look, oops, I'm pushing the wrong buttons here. Here we go. If you're looking at a server or a cluster, it'll usually be a few nodes a few processors put together. Each one has its own memory, and they're connected over some super fast network. And so that. And each of the nodes, again, is a multi-core chip. So it's you sort of have a hierarchy of these things at this point. Sometimes on bigger machines, and I guess these days even on servers, you'll have a graphics card attached to each node. And so on a supercomputer, there could be, I don't know, 50,000 nodes, and each node could have 4 cores, or it could have even up to, I guess, 16 cores, 16 or even 32. And so that's how you get to 500,000 cores on one machine. Some of the words that people use if you're working on a cluster, you're distributing your work. If you're working on a multi-core processor, you're multi-threading. If you're putting things on a GPU, you're usually offloading. And here, actually, you're offloading. Literally, you have to copy some things from your memory here to the memory of the coprocessor. So there is sort of, in order to use this, you pay the additional cost of moving your data again from the multi-core memory to the coprocessor memory. Some of the programming tools that are on each of the hardware. Some things are native. In some sense, you can do anything on any one of those, but if it's not the native thing, it's a little bit less efficient. So on a distributed memory machine, because you cannot access everybody's memory directly, you kind of have to focus on who owns what part of your data and what communication is needed. And there are tools to make that easier. Some of the software there, usually you can be talking over sockets. MPI is a layer that's built on top of sockets. And Hadoop is a popular thing these days. It's another piece that I think it's on top of sockets as well. When we talk about shared memory, here you're sort of focusing on which tasks could be parallel. So you have your serial code, and you're using usually compiler directives to tell the compiler what should be parallel, like a loop should be parallel, or you should be starting several threads and so on. And some of the software here, OpenMP, everybody's probably heard about OpenMP. Threads, fork. Fork is an operating system mechanism that allows you to start another thread without copying the data, unless you have to write to it. If you write to it, then the copy happens. Some other things that are coming up is OpenACC. They're actually trying to go across both the GPU as well as the shared memory multi-core. So basically there are these two these three flavors, and with all this software. I think I'm getting ahead of myself here. About the last 30 years, most of parallel computing research has been happening over here on the distributed resources. And that's when sort of the parallel computing research community was sort of separate from the rest of the world, and they were doing their own thing for a long time and developed many very, very good tools. In the last 10 years, when the multi-core chips started coming out, a lot of activity has happened down here. So all of this is relatively new, and things aren't quite settled yet, too. So things are still changing in this realm. And when you look at supercomputing, what people are doing in supercomputing, they're trying to put both of these together. So on a supercomputer, you will have all three of these levels of parallelism, and so you're trying to use all of them effectively. Now let's take a look at R. What is happening in R? R has really quite a few packages that do something parallel. But if you look deep down, there are really not that many that are sort of the native interfaces to the original tools. So for the distributed memory, the first one that came out was Snow. Then RMPI. Actually, both of these have been there for quite a long time. We just recently built pbdMPI. This is fairly recent, too, because of the popularity of Hadoop. Down here, all of these are really, the magenta things or purple things are compiler directives. And so R is a scripting language, and it's not compiled. There's no compiler. So none of those things are directly available in R. So in order to use any of these things, you have to program it in another language, C or Fortran or CUDA, and that's how you can use the parallelism in there. What I list here are basically interfaces to other languages in R. So the .c, .call, RCPP. OpenCL is sort of an interface to the CUDA language. And I guess inline is a way to write a piece of, say, C code in your R script and have it compiled at the same time. And so that's another place that it's accessible. Multicore is one thing that's different from all of these because multicore uses the system fork to introduce parallelism. And that's actually quite clever the way this was done. So this is really the only directly accessible parallelism in R through on the shared memory architecture. And right now, the package parallel actually it's a combination of Snow and multicore. So the next thing is HPC library. So while all these things that were happening in R, mostly on shared memory, because R, with the exception of Snow and RMPI, R really did not notice parallelism until it had to. Right? That's when everybody started doing parallel things on the shared memory resources because suddenly there were multi-core chips and everybody had to start doing something parallel. The parallel computing community that was working over here in the meantime for the 30 years before that produced a whole bunch of really, really good distributed computing libraries. And actually, some of these are not just distributed. Like Magma is actually for the coprocessors for the GPU. dPlasma actually spans both of these, the distributed memory and the shared memory. So there really are very many. I guess it's mostly the numerical linear algebra community, just down the hall this way. That's where a lot of these were produced. So University of Tennessee has a lot of history in these libraries, and they're still very active. In fact, dPlasma recently got a big NSF grant to continue the development. So in R has been connected to LAPACK and BLAS for a long time. And so one of the things behind the PBD-MPI development was to begin looking at these other libraries and start to connect R to all the work that has been already done. And it works at this low level, but there's all this incredible stuff available, and it's really much better to connect at that level if you can. And so primarily the package pbdmat and some of the other packages underneath that are the ones that connect to some of these libraries. There are a couple of other things too. HypLRM is also a very recent development from the UK, and they connected to the Magma and Plasma libraries. For a while we entertained joining with them, but I guess we still might. But in a sense, when we're using these, Magma can be plugged into ScalaPack, and so it's if you don't have any distributed resources, then this is you might use this directly. But if you're working on some distributed resources that, even though they have multi-core underneath them, this is really the better place to go, because you can still plug in something like the MKL library, or even well, eventually we still don't have dPlasma, but we will sometime in the future. Essentially, you can plug in MKL or ACML underneath ScalaPack in some sense, although MKL actually includes ScalaPack. But that gives you the multi-threaded capability, and you can use 2 levels of parallelism. In that case, that's still sort of a research area. It hasn't been tested very much. We've tried it a few times, but you sort of have to manage the number of instances of your distributed code versus the number of threads you let MKL handle. Let's see. So that's Yeah, and so this is just the PBD ecosystem lives over here. So we have this piece here, and not everything is available through all these libraries. So sometimes you do have to use pbd-mpi and other resources. I guess maybe I'll pause over here. Any questions here? Just some background. Okay, so I'll go on to data input. So data input is a difficult thing. Even if you look at serial R, there's an entirely separate manual just for I/O. And there are so many different ways you can read in the data, and in part it's because there are so many different formats. So some of these, like scan, read table, read CSV, these are for, I guess, ASCII data mostly. And all of these down here are essentially binary data. And the one big difference between ASCII type data like CSV files and binary data is that in binary data you know the format, and so if you want to position yourself 1/3 of the way down the file so you know exactly where to go because it's all the format is fixed. Whereas in a CSV file, you don't know how far you have to go because there could be extra spaces, extra whatever. Things are variable length, and so it's difficult to access things at random. And that becomes important when you start doing things in parallel. So I guess, so to continue, so if you're using pbdR, and you want to bring in your data, you don't have a parallel file system, and you want to bring in data in parallel, you sort of do it in serial here. You read it in on one processor or one core and distribute it out from there. Because if you don't have a parallel file system, it really wants to talk to only one core at a time, or maybe two, depending on your if it's a laptop with 2 cores or 4 cores. I guess it has some things to make it to be a little bit faster if you have 2 cores reading than just 1 core, perhaps. But I'm not sure about that. That's even debatable. So you sort of have to match the number of readers to the number of resources available to give you the data. So if you have, if you're, for example, if you had a cluster, and with say just 16 cores, and you did something like this, where you read it on one of the cores, actually, if you had all the cores trying to read the same file, then the file system would just go crazy because it cannot handle that. It's much faster to have just one of them read it and then distribute it out because the network is much faster than the I/O. So to do this with PBD, so you load pbdmat. Here, basically, you ask if you are processor 0, because this is all happening in parallel, by the way. So this code is executed on all the cores. And if you are core 0, then you're going to read the file. Else, you'll just give it null. And then the function sDataMatrix will do the right thing and distribute the matrix out correctly as needed, using certain defaults, I guess, at this point.
If you want to distribute the same, so let's say you were reading in some other file that every other rank needs, how would you push it to all the other? You wouldn't use say as data matrix. You want
right. If you would just push it out, so you would just broadcast it out.
Okay,
from. So you would read it in on one core and then just say broadcast to everybody. Okay, so so far, even though we were running in parallel, we were reading it in serial. Once you're starting to do parallel data input, if you do have a parallel file system, which is actually the case on many clusters at many institutions, there will be a parallel file system attached to it. Usually Lustre, there are some other flavors available. So there's a whole host of new issues that comes up. So I guess first of all, there are all these different formats. I already mentioned that for something like CSV, it's difficult to read in parallel because you cannot start in the middle and know where you are. And so what you want, you want all the processors reading different portions of the data, right? And you want to be able to tell them where to start. So some of the issues that come up is first how to partition the data across the nodes, and another question is how to structure it for scalable libraries. Scalable libraries like to have their data in a very particular way. And so another question that comes up is whether you want to read it directly into that format or read it in some easier way and then restructure. And so basically what's happening here, this is very hands-on at the moment. It's not that easy. And still there a lot of work is needed here, and we're working on some of that. But I'll show you some examples where things are a little, just some basic examples here. So here is an example where you actually we do have one function that reads in parallel, and it's read CSV. And it sort of reads in parallel because you still need to position yourself in the file. And because it's a CSV file, in order to position yourself in the right place, you have to start reading from the beginning. So you don't quite read it so many times. You read a little bit less, so it's a little bit parallel, but not too much. And the reason we did it simply because a lot of people have CSV files, and it was easy to do. So here again, so you load library. I guess I'm not sure, Drew, is it in PBD demo or is it in, it's in demo, okay, yeah. And so as Drew was already talking about it, you start with init grid because you're doing a matrix. And then you do the read CSV, there's the file name, and all the usual parameters apply. I guess there are some other parameters here, like the number of readers in this case. And then we just print it and finalize. Let's see, I think I have this here. I can try it here. No, wait a minute. Actually, no, I don't. I wasn't going to do this one. Let me not do this one yet. Let me go on to another one. I'll have some examples later. The reading examples are, I guess all I could show you is that it runs. Really, that it's not. I don't think it's very useful. But these scripts are actually available. We'll tell you where these are. And actually, PBD demo has a lot of these in there, if not all of them. So this is, a lot of people use netcdf4 data. And we have, there's a package, PBD and CDF4, And that package is able to read completely in parallel. And it actually can write in parallel as well. Reading in parallel is relatively easy. Writing is a little harder because you have to structure the file correctly. If you're reading it, you can do it sort of almost you can do it independently. You don't really have to know about each other that you're reading the file. But even there, actually, if the reading is done in a collective way, it's a little bit faster. So what happens here? This opens the file. This one sets it up, sets up a particular variable. This is a variable name out of that file for parallel access, for collective parallel access. And then ncvar get is the one that actually reads it. What the user has to do is provide a starting point and how far to read within this specific array. So that's what I mean by hands-on. That you have to know how far out each one is going to read. In the PBD demo, there is actually in PBD demo there is an example on how to write a file and how to read a file as well. So this is just to show you that it can be quite difficult. This is sort of a real example with simply a binary file, and the idea is we have a cube of data, and I have this over here. This is out of a project. So we basically have a big cube of data. That's the blue thing here, and it's actually a piece of the ocean in reality. It's simulating a piece of the ocean, and so we have this big cube, and it's really big. It's 2048 to the third, and I don't have MEMUs here. Drew, do you have MEMUs work? Do you have an R session up? How much 2048 to the third? How much memory? How many gigabytes is that? I forget, but it's pretty big. 64? Okay, so this is a really big file, and it's so 64 gigabytes, and what we're actually storing is velocity. And so you need 3 components for that. So it's 3 times that, and we do it for many time steps. And so it's a really big data set. It's about a terabyte, I guess, altogether. So while developing this code, and the reader that I wrote actually is it just takes a subcube out of here. And reads that subcube out of there. And so the code that I'll be showing you is actually just for that. Let's see, it's over here. So just to give you, so there's the global. You give it the global data dimension. Can everybody read that? Is that okay? Some of the things you give it is the global start, so that the global start would be this point here, and that's global start in all the 3 coordinates. And you notice that over here I'm already my coordinate depends on my rank, and I guess the third. Let's see, where do I get MIDIM? Okay, I messed with the code. MIDIM is actually defined, the order here is wrong, right? So anyway, so you basically determine it from the number of what is my rank and what is my dimension, which my dimension depends on how many instances I'm running, which is com size. So com size tells you how many instances of this code are running in parallel, and com rank tells you which one you are. And you use that information to determine how far you're going to read. So basically, how far you're going to read in this direction, in that direction, and in that direction from the origin. And so that's essentially how you write a reader. You give it these a position and these starting points, and then you have to do some. So blocks 3D is a function that I'll show you later that reads that uses this information to actually step through this array, through this binary array. Okay, and it has the data dimension, my start, my dimension, and the size of each. These are actually this was a single precision file, single precision floats. And then some other things have to happen. So once you read it in, this is basically a vector. So this is stored as basically a vector. I think so. Let me look at that. I forget if I did it that way. Okay. So this is the block 3D reader. That's just this line here is the block 3D reader. And so I probably shouldn't. I won't go into. I'll just sort of highlight a few things here. So first of all, you open the connection. So up here, you open the connection. You open the file as a connection. This line here positions you in a specific place in the file, and this is the actual binary read. And the difficulty here, it's actually not that easy because things are stored in a certain way. So if you want to read this column, it's actually inside this whole file. Well, actually, we're going to start from the bottom. So you start from here, you read up to here, and then you have to skip a bunch to read the next column that's going to be up this way, and skip a bunch again. And the same thing happens when you're going this way. You have to skip bigger bunches. Yeah, and it's basically all hands-on right now. Do it yourself, and that's why it's difficult. And that's what the rest of this code is. So I won't go into that. So going back here, so after you read it in, you have this vector. And so now what happens? I'm actually preparing this for the principal components. What I want to do is I want to take each one of these planes like this and arrange it all as a row of a matrix. So basically, this plane becomes that row. The next slice here becomes the next row of the matrix, right? And I just construct this big matrix out of all of these. And the reason I do that is that if you look at the cube, there are these filaments that are going this way. And so there is stuff that's sort of repeating itself. And when people use empirical orthogonal functions in climate, they're doing it over time. And climate sort of weather repeats itself over time. So you want something that's fairly stationary and repeats itself over time. And that's the dimension that you put down your rows. And so usually it's time that goes down your rows. In this case, it was another dimension this piece of ocean that's sort of rotating, and they're picking up all the certain turbulence happens in there. So anyway, so this is the next transformation here. So let's see, what do I do here? So I take so my rows is the product of of these two dimensions, right? So and I actually take that back. I actually take the transpose of this in that code. Okay, so I actually do the transpose. And the reason I do that is that my matrix is going to be much longer this way than that way, and it's a lot cheaper to deal with it that way, and I can still do the same things. So I have to specify number of how many rows do I have on this processor, how many columns, what's my local dimension, my row by my n column. I have to specify the global dimensions for the matrix as well. And so now I use the local dimensions, my row, my col, to actually shape the local matrix. So it actually becomes a matrix. And now I start with DD matrix. So I give it the data, and DD matrix basically just plugs in the global context. And so I build it all locally, and then I say I have it already connected all up. And so that's what the new is actually a standard R function. This is not ours, but the DD matrix instance of it is, right? I guess it's an S4 method as well. And so now I have this. So I have the transpose of this matrix, and so what do I have? I have it actually chopped up like this between processors. So if I had 4 processors, this would be 0, 1, 2, 3, and the matrix would be in pieces like this across the processors. The final thing with the redistribute here, what I do, I bring it into what's called block cyclic, and this is something that LAPACK likes. And so once I've done this, I can use all the matrix methodology. So it takes quite a bit to get things into the right form. And so now we go into the analysis here, the principal components. So I have my m by n matrix X, right? So this is actually this is my m, this is my n. And to do principal components, you have to center each column, do the singular value decomposition. And what you get out is your left singular vectors and your right singular vectors. And they give some certain nice things. You get n time series if you multiply it by the eigenvalues, by the singular values. You get something that has the same units as the original matrix. And I'll show you how this plays out in a moment. So let's go on here. Anyway, this is just a note here mentioning where this was presented. Let's see. So we've already seen this. The only additional thing here is that I actually do it 3 times. I do it for x, y, and z. I just showed it to you for x, and here it's done 3 times because this is velocity, and we need all 3 components. And so This is the R code. So after you get the data in and redistribute it to block cyclic, you just use it the way you would in R normally. So in order to compute the sort of the velocity, energy from the velocity, or your speed in a sense, you just square each. Each one of these is a matrix, by the way, and it's a distributed matrix, just like this across all the processors. And all I have to do here is simply use R at this point. And the same thing, the function prcomp, the same thing. I don't scale things here, by the way, because everything is in the same units, and so I actually don't want to scale things here. Okay, so once I get the result, how do I plot something, or how do I get it out? Because now I have the result on spread across so many processors. So what I do here is, if my rank is 0, so I guess prcomp is an S4 method as well. So we have a DD matrix method for prcomp. And it takes most of the same parameters as the regular prcomp. So some of the things that happen, so the principle, you get the left singular values and the right singular values, and I say ret x is true. That means that you'll get both, actually, both left and right. The singular values are on every processor. The right and left eigenvectors are distributed across all the processors, because those are really big matrices.
I think there's two methods in R to do principal components analysis, right?
There are.
Correlation matrix, and there's one that does the singular value decomposition.
Right. Yeah.
So a person could first form a correlation matrix.
You could.
That's not the way to do it.
It can be. I think we have. Wei Chen, do you know if we have the correlation? I mean, instead of prcomp. Well, we could. That's right. I mean, we can just plug this into prcomp. Yeah. Yeah.
I'm just saying that once you did that, and you did an eigenvalue decomposition instead of a principal component, you would get the V matrix.
Right.
Then you'd have to convert. You'd have to go do a bunch of linear algebra. So I'm just wondering.
Right. Right. It depends on the size of the matrix.
He's more efficient, so that's what he's saying.
It depends. I would say it depends. But you have to form the cross product matrix too. That's another cost in there. Yeah. And so if you form the cross product matrix here, essentially you only get the U because the VB transpose cancels out. Let's see. So did I? Okay. So here, so you just compute this the way you would normally in R, but then if you want to get something out, you have to plot it. So you only ask one of the ranks to do that. So this thing here, the standard deviations are everywhere because the the singular values are actually not distributed, because that's just a vector, and we decided that we're going to have it everywhere so that everybody has it. And so 0 has it. We don't have to do anything special to get it. Just regular, we take the first 50 components here, get the proportion of the variance explained. We're basically doing a scree plot. Is everybody familiar with a scree plot? That basically shows you that. And so this one we can run. I actually just did it here. We can do this again. So here I do MPI run Can everybody see it down here? Is that good from back there? So MPI run. I use 4 processors. I mean, four threads in a sense. I only have 2 cores. Now, why do I do that? Because I am not reading the original data here. What I did, I already did the reading on another machine because that takes a little bit more, and I did it because it's a big data set, and I saved the local pieces right here. So I have when I do an LS, you'll notice I have these scripts in there, and I have 4 data sets, and so I set it up for 4. And that's really the fastest way. If you have 4 processes, if you want to dump the data and then read it back in, do it exactly the same number of files as you have processors. If you have a parallel file system, because it's really a fast way to read it back in. So I'm gonna run that here now. If you will notice up here, these are my 2 cores. You can see that they are quite. At first, they were not very busy here, and now they're getting really, really busy because they're both trying to do this. It just takes a few seconds here because that's a pretty good size chunk of data, at least for the laptop anyway. And I think it should be done any moment. Yeah, there, and it just finished. So you just, the main thing to note is here that it really exercises both of your cores really heavily here. Whether it's actually faster on this laptop, probably not. If you were actually using 4 cores if you had a quad-core laptop, you would probably be faster than with a single core. Yeah.
How do you get that?
How do you get that? Ah.
How can you easily monitor whether you actually did what you're trying to do and make it usable?
Do a Google search for Raging Menace menu meters.
There you go. Yeah.
Raging Menace menu meters. Yeah.
Yeah, that's it. Okay.
If you work on a Mac.
Yeah, if you look at the task manager, you'll see it spike. So if you just look in the task manager, go to performance.
If you have a PC.
If you have a PC, that is like Mac will. Like if you have a PC, you can see the actual R scripts being instantiated, and then you can see the spike.
But you have to, they're not up in your menu. They're not
You can what's it called? Make them stick. I never wrote task manager.
Okay. So the next thing I wanted to show quickly here, how can we plot in parallel? Okay. So one thing that we can do is if you want to do several plots, you can do each one or more on each processor. We can do that now. To do one plot by several processors, you would have to rewrite the code. That's a little bit more difficult, so we don't do that yet. So here's a function that takes, you have this matrix here, or actually it's this one. And because each one of these slices is actually a column in here, right? This column is a slice of the matrix, and so a slice of this cube, and so that would be the picture that we would want to render. And so this is just a function here that renders a slice. There's nothing parallel here. It's just a regular function. Some of the fancy things that I do here is that I make sure that my colors are zero-centered, and most of the values are a certain color. I guess most positive values are the brown values, and the negative values are the blue values. And that's useful when you're doing principal components because things are unique up to a sign. And so sometimes you get the colors flipping unless you clean it up like that. And anyway, I actually don't use ggplot here. This was I was trying to put this together quickly, and I use the image function. It's the use raster is true. It's fast, and it's probably faster than ggplot as well. But eventually, I'll have ggplot in here. I do use it a lot. Okay, so get and redistribute the data here. So what I'm doing here, I set the dimensions, global and local dimensions, and I load the file. I actually did not put the dimensions of the things in the file. When I save the file, I just saved it as a vector. So those 4 files are just vectors. And so I have to go through the reshaping process all over again. But anyway, you can ignore all this. And so anyway, so this is what happens in the script. And let's see. And here is how I make the plots in parallel. So I don't want to plot everything, so I do some fancy things here that select only certain columns out of this. The one thing that I need to do here is just notice this function right here, gather columns, because this matrix is now actually in the block cyclic form. So I don't really have the entire block cyclic means that things are also chopped up the other way. Okay, and I have different pieces of this on different processors. And so what I actually want to do, I want to again move the data around so that I have a full column on each processor. So locally, I can have a full slice. And the function to do that is right here. Let's see. So what do I do here? I select. So I limit this to a certain number of columns. I don't use all of them. And then the function, the pbdR function, as column block will just do that for you. Okay, it'll take the block cyclic form into this column block form. And so it's really easy. This you should just ignore. This is something that will be fixed later. It's sort of something that Scalapack does, and it's annoying. And it wants to, even if you don't own any data, it wants to have something in there. And so we had to do a little workaround. But we do have a function that will determine if you actually own any data or not. Okay, so let's see. Yeah. And so now we just we plot the components, and there's the script that I'm going to use. Okay, and this one again, it's again reading. I guess notice little meters up there. It's again reading these four data sets. It's reconfiguring it. I don't really have to do all that stuff every time. I could have saved it in a different form and then just reuse the correct form, right? But this is just for illustration. And so what it's actually doing is that each processor is plotting a few of these columns. Okay. It's not. I think it's doing every fifth one or something like, or is it? Yeah, I think it's every fifth one. And basically, some of these columns are getting plotted. So it's so effectively some of these slices are getting plotted. So now it's done. And I'm going to go over here. And let's see, which one did I just do? I did 4. Okay, should I be? Oh, there it is. No, wait a minute. Okay, I think I did the other one. Let me list this here. So I did the 4 plot. So let's take a look which one. Oh, I see. So this one. Wait a minute. Did I think I was wanted to do a different one here. Okay. Yeah. So I actually wanted to do the other one. So this one actually plots the 4 principal components, for the first 4 principal components, and I'll show you that. I'm going to first do this one, which actually does quite a few more of them. So this function actually plots the slices of that. The other function plots the actual eigenvectors. Okay, so this was done. By the way, it also uses a timing function. It tells you how much the script when you see the script. It uses a timing function. And so now here I have all the plots that it made. And so this we can just display these like this, and you can just sort of scroll through them, and it sort of makes a movie. And there are tools that will put these things together for you and make a movie out of it. Okay, so this is the movie part of the talk. And so the other script did the principal components, plotted the singular vectors, the right singular vectors. And I guess these are really not movies. These are orthogonal components. And in fact, you could, if I took these first 4 components and weighted them properly, their sum would approximate this movie very well. Yeah, so that's one way to think about it. And the reason it does, I didn't show you the scree plot also. And this is what actually happens in the scree plot, that you can see just the first 4 components already. So it's, let's see, 1, 2, 3, 4. So 4 is about close to 90% of the variability. So you'd get a pretty good movie out of the 4 components only. Let's see, it's time for a break. I was going to do I think I'll skip the redistributions, but the scripts are there, and we will post them later for everyone to get.
Can you just relate back to the original problem, what these components are? Is this
Yes.
first principal component, is that for like sort of like the kind of total energy across the whole? I don't know if there's slices or there's depths.
Right. So you can there's so in this subcube there is a certain amount of variability. If you want to you could approximate the subcube with just the 4 components and one, let's see, 4 components and 4 weight vectors. and those together would give you an approximation of the entire cube. So in some way, so if this is the full matrix, I would have just 4 components. If these are, so this would be, okay, 4 vectors like that, and 4 vectors that are the same the other way, right? And the product of these two would approximate this matrix, which is actually the entire volume here.
So is the picture one, is the picture like a filtered or simplified projection or one sheet, or is it?
Yes, yes. The picture is one slice here. Yes. Yeah. Any other questions?
So that's sort of a compression.
It's sort of a compression. You can, and so the idea is that if you have a lot of data like this, you can make a big movie in parallel, right? So you could. Some of these things take a while to render, and so if you have a big data set, you could do this more quickly. It would be more or less interactive, I guess, in making it.